In this video, we're going to start Unit 8 Acquisition 3, which is all about acids and bases. So today we're going to write down some definitions of acids and bases, and then you should be able to identify them. So a definition that you should be familiar with is the Arrhenius definition of acids and bases. So the Arrhenius definition of an acid is that an acid donates a hydrogen ion, H+, in water. Whereas the Arrhenius definition of a base is that a base donates a hydroxide ion. Hydroxide is OH minus. So this is actually a pretty good definition. Acids do donate protons or hydrogen ions in water, but there's a limitation to this. This only works for substances with those ions. So an example where this definition does not work is ammonia. Ammonia is NH3. Ammonia is a base without hydroxide ions. So we need a better definition, one that is more inclusive. So that brings us to the Bronsted-Lowry definition. Bronsted-Lowry said that an acid donates a proton, H+. But instead of saying that the base donates hydroxide, the base is going to accept that proton. The base accepts a proton in water. Since the Bronsted-Lowry is more inclusive, it's going to include bases that don't have hydroxide ions. This is going to be the main theory we will use. So know both of them. But when we're doing examples and it asks you, to identify the acid and identify the base, we're going to be looking for the Bronsted-Lowry acid or Bronsted-Lowry base. You should also be familiar with the term conjugate acid-base pairs. You're going to have to identify conjugate acid-base pairs. This will be a pair of compounds that differ by the presence of one proton. So let's look at an example where you're going to have to pick out the acid and the base and then also identify our conjugate acid-base pairs. HNO3 plus H2 yields H3O plus NO3 minus. So the first thing that I do is I identify conjugate acid-base pairs. I'm looking for a pair of compounds that differ by the presence of one proton. So HNO3 and NO3 minus differ by one proton. H2 and H3 differ by one proton. This is a conjugate acid-base pair. This is a conjugate acid-base pair. When you're identifying the acid and the base will always be on the left-hand side of the arrow. So we need to figure out which one is the acid. The acid is going to donate a proton. So which one of these donates a proton? HNO3. It donates its proton, and now it is NO3 minus. It lost a hydrogen, and it lost a positive charge, so it went from neutral down to a -1. We would say HNO3 is the acid, NO3 minus is its conjugate base. It's called the conjugate base because when this reaction goes reverse, the nitrate ion now accepts a hydrogen. So when this reaction is going forward, nitric acid is the acid. It is donating a proton. When it goes in reverse, nitrate is now accepting that proton. So nitric acid is my acid, nitrate ion is the conjugate base. That means hydrogen is going to be the base, but let's make sure. The base accepts a proton. H2, it goes up to H3. So hydrogen did accept that proton. Hydrogen would be the base. Hydronium, H3O plus, would be its conjugate acid. Let's look at another reaction. All right, first thing I want to do is find my conjugate acid-base pairs, figure out which compounds differ by only one proton. NH4, NH3, they differ by one proton or one hydrogen. H2, H3, here's a pair here. The acid is going to donate a proton. So the acid would lose N4 down to N3. I'm sorry, H4 down to H3 or H2 up to H3. Which one is donating or losing the proton? The ammonium ion is. It's going from 4 hydrogens down to 3. This would be my acid. NH3 ammonia would be its conjugate base. My base is going to accept a proton. So water is base, 2 hydrogens, it accepts a proton, now it has 3. Hydronium would be its conjugate acid. Let's look at one more. Carbonate plus water All right, try this one on your own. Pause the video. When you're ready, come back and see how you did. All right, let's find my conjugate acid-base pairs. So these two species differ by only one proton. H2, H1 differ by one proton. All right, so the carbonate ion, here it has no protons. Here it has one proton. That means carbonate accepted a proton. Carbonate would be the base, and this would be my conjugate acid. I have two hydrogens, and I go down to one. That means water lost a proton. If it's donating a proton, water is acting as an acid. Hydroxide would be its conjugate base. Notice that in our second example, water was a base. In the third example, water was acting as an acid. They have a special name for that. Amphiprotic. These are molecules or ions that can behave as either acids or bases. All right, there's a few more terms that I want you guys to be familiar with. And we talked about this a little bit when we did titrations. Acids can only donate one proton at a time. And a few terms to know. Monoprotic. If I had a monoprotic acid. A monoprotic acid only has one acidic hydrogen. It only donates one H+. Maybe something like hydrochloric acid. Doesn't have any more protons to donate. We can also have diprotic acids. Diprotic acids can donate 2 hydrogens or 2 protons. Like sulfuric acid. But it can only donate 1 proton at a time. So even though sulfuric acid has these 2 protons, we can only donate 1 at a time. So if I pull off that first hydrogen, that leaves me with 1 hydrogen. This compound is neutral. If I take away +1, it's going to be a -1. Now I could lose my second hydrogen. And again, if I remove a -1 charge, it goes down to -2. We could also have a polyprotic acid. Poly means many. Protic for proton. So we can donate many protons. We could also call this a triprotic acid. Again, even though there's 3 protons, we can only donate 1 at a time. If I pull off 1 proton, I lose a positive charge. This goes from neutral down to a -1. If I pull off a second proton, this is going to go from a -1 down to a -2. I lost another positive charge. I have 1 more proton to donate. If I lose another positive charge, it's going to go from a -2 down to a -3. The last thing that we have to talk about today is strength of acids and bases. Strength of acids and bases. Strength is determined by the position of the dissociate equilibrium. So we're going to be looking at equilibrium constants, Ka for acids, Kb for bases. And their strength depends on their dissociation. Strong acids, bases completely dissociate. Remember, dissociate's just like a fancy word for breaking up. It's going to completely dissociate into its individual ions. Strong acids and bases completely dissociate in water. If you have to rank acids based on their strength, the way you can tell an acid is strong is they have a very large dissociation or K value. If it has a big Ka, that means it's going to be a strong acid. Weak acids or bases. Again, it depends on how far they dissociate. Weak acids only partially dissociate. Dissociate only to a slight extent in water. So if strong acids or bases have a large dissociation value, weak acids or bases have a very small K value. Important to note, strength does not correlate to concentration. Common misconception. Just because something is highly concentrated doesn't mean that it's strong. You can have a strong acid like hydrochloric acid that could be very concentrated, but you can also have a very dilute hydrochloric acid. Hydrochloric acid is strong because it completely dissociates regardless of its concentration. Two other things to note. Stronger the acid, the weaker its conjugate base, and same with bases. Stronger the base, weaker its conjugate acid. So that's an important trend to keep in mind as well. Alright, I know this has been a long video, but I want to go through just one more example problem. Rank the following acids from weakest to strongest. And just for extra practice, determine the conjugate base of each acid. Alright, so we are going to rank from weakest to strongest. The higher the Ka value, the stronger the acid. The lower the Ka value, the weaker the acid. Make sure you pay attention to your scientific notation and not just the numbers. The vast majority of acids and bases are weak and they're going to have a Ka less than 1. So you need to pay attention to scientific notation. So 6.2 times 10 to the negative 10th would be the smallest Ka value, followed by 4.0 times 10 to the negative 4th. My biggest value, therefore the strongest acid, 1.2 times 10 to the negative 2nd. Remember that acids don't need a proton. So if I want to write the conjugate base, all I have to do is pull off a proton. But remember, it has a charge of +1. So if I have an acid that is neutral and I pull off a charge of +1, the conjugate base would have a charge of -1. Let's pull off a hydrogen. Again, we lose a positive charge. It goes from neutral down to -1. Pull off a hydrogen, -1.